We want to talk about post-harvest grain management. That's how it's generally referred to throughout the Corn Belt nowadays. Grain drying and storage, maintaining quality grain. Because, as you know, when you put grain in storage, it's not going to really improve the quality, right? You can only maintain the quality of the grain that you put in that bin or that covered pile, or we'll talk about different structures that we're seeing across the state. But I think the reason we need to talk about this, of course, is that there's quite a bit of an expansion, and we'll look at some numbers as we go. It's increased storage across Kentucky. It's even more widespread across the U.S., of course. If you drive through the countryside, you see a lot of shiny metal bins out. Some of these are in existing facilities, some are in new facilities. I know a lot of the expansion, the production in the storage area is certainly coming in this direction, and to follow the production, right? So that's another reason we didn't want to talk about it. But there's obviously some safety considerations. Oftentimes in the past, I've talked about the safety aspects at the last part of the presentation, but because of the importance, I've moved it up to the front today. Then we want to start taking a look at some physics, some biology, how insects and moles interact with grain, how grain interacts with air, and that should be time, storage time. I don't know how that E got dropped there, but towards the end of the presentation, I'll talk about temporary structures, but on the way, I want to hit pretty hard on an IPM version of grain storage, and we refer to that as S.L.A.M, which stands for Sanitation, Loading, Aeration, and Monitoring. Okay, it's just kind of an acronym we use to summarize the activities to reduce pesticide use as much as possible. We want to use pesticides kind of as a last resort with all these other practices, which we'll discuss. And then I'll close with by sharing some web resources. One of them, I brought an example as we close that out. But obviously, this picture was not taken in Kentucky, but it represents many of the structures we want to talk about. Okay, we have obviously large metal grain bins, small ones. We have some concrete silos you see here in some facilities, not on farms, of course, but at elevators. And on farms, we're seeing some smaller piles, but what we call it's a covered outdoor pile. These can be built so that you can have an aeration fan in those, and then you're pulling the air down through the pile. It'll do two things. It'll cool the grain, but it also holds the tarp or the cover down on the grain pile, otherwise the wind's going to blow it off. You have to weigh it down like you would a silo, horizontal silo. A more permanent horizontal structure would be seen on the upper right slide, part of the slide here, and what we call a warehouse or a flat storage. Generally on the farms, they're smaller than that, but I've done some work to kind of support that activity as well on the farm. So we'll talk about that as we go along. I want to give you a little flavor of what we're seeing in terms of storage, and this is numbers I pulled out of the Kentucky Ag Statistics Service, of course. So it's easily available, but we're looking at a trend of storage both on-farm and off-farm in Kentucky. This is total storage capacity back from, so it's for the last 17 years, from 99 up to 2015, and then these will be updated for this year. But what's interesting for Kentucky is this blue line to me, is that's the on-farm storage. Okay, and then we're looking, of course, for Kentucky, we're talking in terms of millions of bushels. There have been some years when we've seen a steady trend as much as like 5 million bushels built per year. This is as good as the data that the farmers provide. Understand, okay? I know you're aware of that. But I think it's a good indicator. We are seeing an increase in Kentucky. We know that. You know, exactly how much to the bushel, probably don't know that, but this is a trend. And the other thing that's interesting for Kentucky is we have more on-farm than we have off-farm. We have more on the farm than we do at the elevators. 3 times as much, as a matter of fact. So in other words, our total storage capacity now is actually for the most recent data, 2016 is around 290 million bushels in Kentucky. 3/4 of those are stored on the farm. And then 1/4 of them will be in the elevator. So, you know, we're seeing here on-farm capacity exceeding 200 million bushels. So it puts a lot of responsibility to keep that grain in condition on farmers, not professional managers, right? although I think they could certainly be classified in that regard because of all the bushels that they say grace over. But and then in turn, I think they need resources from Extension on how to manage that grain, because there's a lot of value represented in those stored bushels, right? So that's the situation for Kentucky. If we look at a national picture here again, I know when we were adding about 5 million bushels on the farm per year, Iowa was adding about 12. So that just speaks to their level of capacity in Iowa versus Kentucky. And you know, if you're going to look at Kentucky, if you remember, we were down here under 1 billion, right? Well under 1 billion bushels. But nationally, we've seen a trend of an increase, and most recently, a fairly sharp increase in the last 10 years, 10, 12 years. And we're seeing nationally, now this varies by state, but Kentucky really, in the region, we have more on-farm storage, a higher percentage of on-farm storage than any neighboring state, any other state in the Corn Belt, for a matter of fact. The only other state that has close to the same, like 75% of on-farm storage would be Washington, in the numbers that I've seen. So Kentucky is a big player for on-farm storage in terms of capacity or percentage there. But nationally, it's more like a 55-45 split, okay? And so in other states, there's more active programs from the industry, okay? They have a Grain Elevators and Processors Society. They're meeting actually this week in Denver. And they'll have it's like you take the Farm Machinery Show and you put all the vendors that have anything to do with grain handling and storage and drying in one spot. And that's the Jeep Trade Show. So I encourage you to go. So they've been in Louisville, they've been in St. Louis, they've been in Nashville, they've been in spots close. They move that meeting all around. So keep an eye on that one. We'll talk about that at the end as a kind of plug for that, but as another resource, because they do have some online courses that they offer. And most of those courses are presented by land-grant professors like myself. So the other piece of this, you know, we've looked at the capacity. We want to also look at, you know how what the incentive for storage obviously is multifold. You have a lot of reasons why you want to put up a grain bin. One is to keep the combines running. That's the most, I think, for a lot of farmers, large farmers especially, that's what they'll tell you. Well, you know, before I had storage, I had to wait at the elevator. Combine was waiting in the field. But with on-farm storage, now I can keep my trucks rolling, I can get a bigger combine, everything gets bigger. Bins get bigger, we'll talk about that. But then how does that impact the price? Well, the price fluctuates, obviously. This is just an average, and again, this is from Kentucky Ag Statistics Service, about information for corn. This is cash prices, and each month they report the statewide average. And that's what I've done, and just plotted those for some select years. And I started in September, so more or less the crop year is how I've plotted this. And you can see January, February, you see a little bit of an increase over harvest time prices, and that's a lot of time, that's when grain is sold, as you know from your county. You see a lot of truck movement January and February, especially when you're traveling in the western part of the state. But, and again, I say that production and the need for storage, I think, is moving more in the center part of the state. But that's the incentive. You have a little bump in price, and with that return, you can pay for storage. It's been pretty flat for corn the last few years. Previous years had a little more margin there. Soybeans, you can get some good years. You can get some years when it's kind of flat, and you get some years when it goes the other way. But I think just to kind of emphasize what can happen, you can see a $1.50 increase, for example, for soybeans. So you can start paying for storage pretty quick with those type of price recoveries in the market. Having said that, okay, you got to keep it in good condition, as we were talking about. So here I've seen several examples of where farmers have not paid attention, maybe as well as they needed to. The grain spoiled during storage and has lost value. You probably can't see this too well, but we're seeing some sprouted grain. This could be in top of a bin which had a leak from a downspout or off of a roof vent, that kind of thing. Anywhere you get moisture buildup on the surface of that grain, it's likely to sprout. Or if not sprout, then it's at least likely to start building some mold. You'll see that probably first. And that's shown in this slide, which is kind of washed out. But with the sprouted corn, there's some mold damaged kernels around that area. And so depending on how large of an area that is, you may have to haul it out to the field. If it's a small amount, probably can blend that in. A lot of folks, that's how they handle it. But you got to be careful with that because it could have some mycotoxins in it, could be damaging to feed as a feed. Another example I ran into was we're in a bin rescue situation several years ago, but a fellow was working in the bin by himself. He was caught in the grain flow about up to his chest. At the end of all the EMS activity and the fire department and the helicopter that showed up on the site after all that was settled down, they brought him out of the bin on a backboard. They took him to the hospital and checked him out, and he was back home that evening having dinner with his family. So it's easy to tell the story because there's no one was hurt in the situation. But the problem of the whole deal was he had a large chunk of grain. When he first started unloading the bin, he didn't see all that. All he saw was just what was submerged in the top. So he thought, well, I can just push that through, break it up, and it'll flow through with the good grain, get out of the bin. Didn't realize it was such a large mass below that. It's like an iceberg, right? So that can happen. And we'll talk about how that can happen as we go along and how to prevent that. But we do have a lot of value represented in our stored grain. I'm often asked, how often should you check it? And if you think about if that was a bank account, you got a 10,000 bushel bin. That's a small bin these days, but even $3 corn, right? You got $30,000 sitting there. How often are you going to look at that? All right? Or if you got the average bin size that's sold today is about a 50,000 bushel bin. That's nationwide. So now if you get, let's say beans are now $10, okay? Now it gets up there. Those zeros can string out pretty good. So it gives you some motivation to look at the grain, check it, and be sure it's in good condition. And so what you want to look for, obviously, we're showing here and why as we go through. Obviously, there's a lot of caution. You can't, every grain bin built today has placards all over it all around the entry points. You know, don't enter it without proper precaution. So that's always a concern and well deserved. But I think if you take the right precautions, you can certainly check grain without having to go in the bin, for one thing. But if you do have to enter the bin, then you want to exercise a lot of extra caution. We'll talk about that a little bit. The main points here, I think, when climbing, anytime you're off the ground on a farm or anywhere, it's a good idea to have a climbing harness with a large hook lanyard on it where you can hook that onto a handrail or something sturdy. These fellows have a beam access to that. Good idea to have dust protection as well as a minimum for PPE supplies. I have a list here as we go along. This is an older slide taken before we were more concerned about climbing, right? They don't have a harness on, but these guys on the right were actually preparing the bin for fumigation. So they were hauling up all the equipment for that activity, and some of the safety devices weren't in place when that picture was taken, but they were in the process of getting the bin ready. So another tool we have available nowadays, it was not available when that picture was taken before with that large chunk of grain in the bin. We have these coffer dams, and some folks refer to these as rescue tubes. Simply, that's actually a brand name, like a Kleenex to a tissue kind of relationship thing, right? So you have metal, plywood, plastic, different colors, different manufacturers, but these all have a similar design. They're basically come in 4 sections, so you can get them through the manhole and assemble them in the bin. And when you would place those around someone that was partially submerged in the bin, and you scoop out the loose grain around that victim, and then they can extract themselves, because if they just have a rope, you don't want to pull them out, right? You got to relieve that pressure. Even with a harness, you got more bearing, more surface area to pull against the victim, but there's too much pressure. You got to relieve that pressure and get the grain away from the victim. So that's what these are designed to do. There are some plans for plywood and rope system that you can build on the farm. That's another option. But I just want to point that out as I think if you have a lot of grain on hand, it's probably a good idea to have a coffer dam somewhere in the shed where you can have that access to that if you need it. And obviously, You don't want to go in the bin if you don't have to. There are some good reasons to go in to check the quality, as we talked about. Oftentimes you can get a sample from the edge of the bin, okay? And then you can reach in there with a probe and get a sample. There's some other tools we'll talk about. But you certainly want to lock out and tag out, shut off the unloading equipment before you enter the bin. You want to work in pairs, as we showed there earlier, so that you have some help if someone gets in trouble in the bin. You want to use a respirator or a dust mask to protect your lungs from the dust. It's always a good idea, of course, to have a third person on the ground, cell phone handy in case you have a problem, have a bridge or something like that encrusted over the grain mass that you don't expect. And that's why you don't really want to work in the center of the bin, okay? You don't really know what's going on underneath that. You can't really see what's below the surface. So some of the tools that I think would be handy for checking grain, obviously you want to have that lockout, tagout kit, and you want a key in your pocket before you climb up on the bin, wear your harness and your mask, your respirator. Have some way to collect samples when you're at the manhole so that you can take those samples, put them in a bag or a bucket, and it's easier obviously to work off the ground. You'll get a better moisture reading if that grain sample is in a bag and then warmed up to room temperature rather than measuring it cold, okay? Moisture meters have some temperature compensation on them, but it's hard for them to compensate for a 50-degree temperature difference. So obviously a thermometer. I brought along a small hygrometer. It's a temperature and humidity sensor. These cost about anywhere from $2 to $8 on Amazon or eBay. And we're using it in some other work, and I'll show you some other uses for those, but it's a low-cost way to kind of just monitor what's going on inside the bin. Temperature probes can be used, digital or dial-type probes where you can insert in the grain below the surface. That's usually where the problem occurs, as you saw in that one slide. And most often, the problems are in the center, and we'll talk about why that happens. Humidity probe, as I said, they're not so common, but there's ways to work around and get a pretty good measurement of the humidity in the space. Okay, so now we want to talk about the physical side of grain management and the factors that affect storability. The first thing and the most important thing is moisture. If you control the moisture, you're going to control a lot of problems. The second is temperature, so you want to get it dry enough, you want to cool it out as quickly as you can. We'll talk about when that should happen in Kentucky. You want to minimize the broken corn and foreign material in the bin because that blocks airflow, okay? And if you think back to that chunk of grain, it had a lot of broken grain in that mass and allowed it to heat, and then it just kind of started solidifying. Oxygen availability can impact storability. Some of the grain bags we're seeing it's not a full-on hermetic, what we call hermetic storage, but I would call it a partial hermetic. You need more than one layer of plastic to have a true hermetic seal, okay? Because there is some oxygen exchange with that one film of plastic in the atmosphere. But if we can displace the oxygen, we can control the storage environment. If we have broken corn and foreign material in the grain, well, we can dry it a little lower, cool it a little lower, and have a little more storability, okay? So we can get around some of those problems with management on that side. That often costs, obviously, to dry it out, but it'll give you more storage life. So here's a table of allowable storage time for corn. It's predicated on 0.5% of dry matter loss. Okay, so if you have 0.5% of dry matter loss, you're going to lose a grade factor in the USDA grade scale. You're going to go from a 2 to a 3 if you have 0.5% of dry matter loss. If you're harvesting grain, and it doesn't happen so much up in this part of the state, but out in Fulton County, it's not uncommon for them to be harvesting corn when it's 80, 90 degrees, late August. They're out there combining. And the corn is 26% or more. You've only got 2 or 3 days before you got to get that corn down to 16% or lower to safeguard it from mold activity, okay, and damage from mold growth. Because once that starts, then insects can come along and it compounds a problem, or vice versa. If insects are damaging the grain, then the kernels are exposed and mold spores can attack that soft endosperm in the kernel, okay. So that information is available. It's published in the handbook, widely available on the web. and we'll have it on our website, of course. And we can actually fill in some of the gaps that are shown in the table here, just to kind of give you a flavor. But the other thing I want to show here is that as you're cooling grain 10 degrees, no matter the moisture content, you're almost doubling the storage life. Okay? So the take home from that, obviously, you want to dry it as quickly as you can, and then you want to cool it as quickly as you can, because then you're going in the right direction of maximizing the storage time. Okay? So what can happen if you have problems with molds and insects? Well, you have heating. Ultimately, you can have some price discounts at the elevator. You may have loads rejected, as we said before. If you're holding seed corn, if you have damage to the kernels, mold it's generally going to attack. If it's an intact kernel, the mold mold activity will often occur at the tip, right, where the germ is. So you have germination loss. So you want to guard against that. And dry matter loss, obviously weight loss, you're losing test weight, you're losing market weight. So another reason to guard it. So we're looking at here the temperature bands, or how insects react to temperature. They like it warm for the most part. You can see they really like 80 to 90 degrees. That's their optimum range. Get much above that, it slows them down. Get much cooler than that, it starts slowing them down. So generally in September in Kentucky, we have opportunities to start cooling our grain to 60 degrees and then lowering it 10 degrees a month after that. Okay? We're not always harvesting that early in this part of the state for sure, but it's still the same. You want to cool it out as quickly as you can. If you're in a bag, you want to harvest it dry and put it in there cool, because you don't have any option to aerate or cool it out in the bag. Okay? We'll talk a little bit more about that, but it gives you some temperature ranges here for insect activity. Another concern, obviously, is mold activity. And for the most part, with molds and fungi, if you control the humidity in that space, you're going to control the mold activity. And the way we control humidity in the bin is to control moisture, right? Because grain interacts with air, and we'll take a look at that as well. But the bottom line here on moisture control, humidity control for mold activity, is 70% or lower will hold mold growth in check. Okay? That's all you need to really take home on that. I will say quickly that we have reloaded our specialist in Princeton. We have a plant pathologist there, Kirsten Wise. She and I were in a program along with Raul Villanova, entomologist at Princeton, and Todd Davis, and then an economist. So I think it makes a pretty good team, and I think we'll have more opportunities. If you would like our team to come to your county, let us know, okay? Because we'd be glad to come and talk about the post-harvest. And I especially think that message needs to be moving its way up more so in this part of the state. A lot of the western Kentucky folks, they've had a lot of experience with stored grain. Maybe we can bring some of them with us to share their experience, okay? But I think it'd be a very powerful program. But as we're putting this together on the engineering side now, we want to look at how grain interacts with the air. You know, if you have high moisture grain, it's going to transfer that moisture to the air, and what really drives that is the vapor pressure. Now, we can't really measure the vapor pressure directly, but indirectly we can get an idea by knowing the moisture content of the grain and the humidity of the air. So in time, in the field in the fall, in time that moisture is transferred from the grain to the air, and the grain dries. Of course, if you're out in the, you wouldn't know. If you're inside a bin or something, then you can measure the increase in humidity. But outside, you wouldn't be able to measure that. But you're going to see the moisture loss, and that's what's driving it. So in time, grain is going to come in equilibrium with the air. Okay? And then at that point, the vapor pressure is equal. And when that actually occurs for corn is shown here. All right? So at 60 degrees, at 80% humidity, grain will dry to 17% moisture, but no lower. Right? So we have to wait for it to either cool down, dry down, or we're going to take it to the bin and dry it ourselves. Right? Because we don't want it to be in a bin for several days and mold activity start to occur in the top of the bin. That's where the trouble can start. Right, soon after harvest. So we got to kind of take those things into consideration. So that's a picture for corn. Other grains have different relationships, obviously. What I want to do next is show you the three center columns. We talked about 70% moisture or less will hold insects or mold in check, right? Obviously, the cooler for molds and insects. But if we take these three columns and expand them on a graph, that's what I've done in this slide. So here we are at 65% humidity at a wide temperature range from 30 to 100 degrees. And if you're below that, you're in a little safer condition. You're about 60% humidity, okay? Or above it, you're at 70, and above 70, I think you could be at risk, okay? But in the wintertime, our average temperature in Kentucky is 35 degrees. Well, where does that hit the 65% humidity line? Well, about 15.5%, okay? You can store corn in the winter in Kentucky at that high moisture. But if you're going to hold it in the summer, our average temperature, July and August, this is the average monthly temperature, is about 80 degrees. So yeah, in the summertime in Kentucky, we want to hold corn at 13% to keep it in good condition, is the take-home message on that. And so every grain has its own shape of the curve, and the only one I'm going to look at next is soybeans. I do have curves for these on grain sorghum and wheat as well, of course, but those are on the website. But so just for soybeans, they're about 2% lower in moisture at the same temperature and humidity condition. So 13% for soybeans and 13% in the winter, and about 11% in the summer is where it hits that 65% humidity line. Okay? And from those conditions, we then derive these, what we ascertain as the safe moisture levels for the storage period shown. In the fall of the year, it's okay to hold grains at a little higher moisture. If you're going to sell in the spring, you need to be a little lower, but if you're going to hold in the summer, you need to be quite a bit lower. And with the price of corn, that water loss is going to cost you about $0.05 a bushel. Okay? So you got to be sure, if you're going to hold corn in the summer, that you, think back to my price curve that we showed earlier, you want to be sure you can recover that cost that you have to dry it down to hold it in good condition. Otherwise, there's going to be some risk involved, right? Because of the physics and relationship with grain and air. But obviously, you want to check the moisture and the temperature going in. That indicates the storage period for the crop, okay? You want to minimize the broken kernels, and so you want to operate the combine and the auger so that you don't have mechanical damage to the grain as it goes from the field as it goes into the storage bin. Farmers are often a little more interested nowadays in screening grain for mycotoxins. The screen kits, the ELISA kits are a little more affordable. You can test grain for anywhere $6, $7 a sample. If you're selling to a livestock producer, which I think is a pretty good option in this part of the state especially, but it pervades the state. But if you can show them that your grain is below a certain level, then it's hard to argue that. The value of that. If you're going to hold grain for a very long time, it's a good idea to clean it, because then you're going to remove those broken kernels, and along with that, in some cases, the level of mycotoxins that you might have in the grain. And so then it leads up to this acronym we talked about earlier, S.L.A.M, Sanitation, Loading, Aeration, and Monitoring. We're going to go through each point, and it's an IPM approach to minimize the use of pesticides on the farm. And so it's, think of it as a more sustainable approach, because it's going to save you some money, be better for the environment as well. So on the sanitation piece, we want to think about everything that the grain is going to come in contact with from the field as it goes to the bin, right? So the combine, the trucks, the carts, dryers, augers. Sometimes a little pocket of grain will be left in the trough of an auger from the previous year. You want to be sure and clean it out, because that can be a place where insects can grow and thrive over the summer months or when it's idle, and then you're going to reinfest your new crop coming in if you don't clean it well. So that's the idea behind that. And obviously the bins themselves need to be cleaned out really well with a shovel, broom. If you got a vac probe, that's a really good tool. It's a good idea to fumigate underneath the floor to control insects in that area. Okay? And that way you're using a fairly small amount of pesticide just in that one area. Okay? You got to do a good job of sealing for that to be effective. But those points are all important. And obviously outside the bin, you want to remove any old machinery. I've seen a lot of old hay balers, right, around the grain bins. That's a good place for a rat or a mice family to make a home. And if they're that close to the bin, they're going to find a way there pretty quick. And it's a good idea to keep those areas well mowed as well. But you want to remove old equipment away from the storage bins, mow the area, keep them well mowed, and then monitor it. You can put rodent traps out to control and monitor the activity. And then we want to go to loading. I've seen bins that are filled to the brim. Last year especially, we had a big crop. And I've seen soybeans coming out of the vent holes, the air vents. You get a little pile of soybeans on the ground where they've overfilled the bin. We were working with a farmer in X County, between here and Princeton, how about? And we were doing some grain packing work, so we wanted to measure, get a lot of good measurements of the surface. And he said, yeah, sure, come around. Well, we couldn't even get in the bin. We could measure the slope of the roof and measure the bin, but that was, then we had to reconcile them with the test. But we got it done, but it was just, when you're thinking about that for long-term storage especially, you're going to interfere with airflow. You're going to block airflow. You're not going to get air movement through a bin that's overfilled. That's the point on overfilling. There's some other points we'll go along, but part of that and part of the loading piece is you want to monitor and manage the trash and the fines, because if you remember back to the slide I showed earlier with that spoiled chunk of grain in the center of the bin, that started with trash and fines blocking the airflow. And then that allowed it to start heating. And that allowed the insects and the moles to start growing. And then it just kind of expanded from there, the hot spot that was, and it went unnoticed for several weeks, obviously, even months in that case. And that's why I say, if that grain had been cleaned, monitored more regularly, it could have been avoided. If you want to use a spreader on small bins to distribute those fines, get better air movement through the grain. If you can't do that, especially and even on large bins, I think you're going to get better distribution of the fine material if you draw that down periodically, not just once at the end of the harvest, but periodically through the harvest period for large bins. Smaller bins, you probably can wait till the end after it's filled. But this graphic shows a couple things. One is we have a concentration of fine material in the center. Okay, so it was filled. They didn't check it, say, just for argument's sake, and then they turned on the fan and they cooled the outside area quite well, but the air in the middle didn't penetrate as well. Actually, it can take twice as long for a cooling front to pass through the middle if it's packed with fines, because you have more depth, you have smaller air spaces in the grain, so it's a lot more resistance. And when you double the resistance, you double the time it takes to push the air through. So that's kind of indicated by the size of the arrows there. And we'll talk about how to work around that. So this is showing then a graphic. You can see if you core that bin and draw it down, so the diameter of this inverted cone is about a half to a third of the diameter of the bin. That's a good rule of thumb for coring it, okay? As I said, for small bins, you want to core that after it's filled. For large bins, you want to core it periodically 2 or 3 times a week. Because, I mean, with harvest capacities, okay, 20,000 bushels a day used to be a good day, right? What is it now in Lyon County? Some of the 50,000 bushels or more. You're going to fill a 50,000 bushel bin in a day in some operations, and more than that sometimes. So when you're working that hard, you may want to core it even more often, because you don't want to wait for it. At large bins, you don't want to get it full before you core it, okay? Because it's hard for it to get it all out there.
So you're coring it as you fill it more often?
Yes, for large bins. Yeah.
But you don't, after it's filled?
After you still need to core it after it's filled.
So how much are you taking out?
Well, that's a good question, and it depends on the size of the bin, but you want to try to remove just about that much each time, okay? You can put it, it's best to put that in a separate and then spread that around, okay? A lot of folks just put it back in the same spot. Well, it's not going to be transferred very much. It's not going to be distributed very well if you do that. Yeah, okay. So I've got another, I didn't bring this, but there's another slide that shows repeated coring for large bins and how you just take it out a bit at a time, and then you put that in a separate bin where it can spread out. Okay. But it does three things if you core it. You remove the fines, you create some headspace ventilation, improve that, but you also create some space to work if you need to. Okay? So to me, it's a trifecta. Yeah, you get three pluses out of that one activity. An instance shown here is with a cooling cycle isn't pushed all the way through the top. We'll talk about aeration in a minute. But, or if you get some moisture that condenses off the roof and back on the grain, you can get a buildup of moisture in the surface in this area shown here, and you can get some spoilage in that area alone. That's an easy area to monitor. But just looking at through the hatch, you can see if there's any problem there. You can reach in and grab a sample and see if it's increasing moisture. That'd be the first indicator.
How far down, please, take the sample?
Yes. You want to sample as far as you can. I mean, to get a really good sample, you want to sample as many places as you can, as you can do it safely. Okay. And again, before you go in there, you got to lock out and tag out. Okay. But I worked with a fellow at I don't know if you know John Consular. He works at ADM out of Henderson, and he works with like 300 farmers. And they have a crew that go around. That's part of that's their job, is to check the quality of the grain because they don't have that much storage on their facility, so they rely on the on-farm facility. I want to go back to this in a minute. But so they sample. They have a vac. Actually, they can go well below the surface, and you need something like that to get far below the surface. But just for general probing, I think a compartmentalized probe or a deep cup probe would be adequate. And you probably want to sample a concentration of samples in the center. That's where the problem is most likely to occur. Okay. So this next slide is an animation of how aeration front moves through grain. If you're pushing air up through the bin, of course, like most systems run, you can also reverse it. You can pull air down through the grain. It would take the same amount of time, roughly, depending on the ratio of the fan size or the horsepower on the fan and the size of the bin. Okay, we'll take a look at how you want to calculate that or how to do that. This is an example. Well, first of all, the rates we're showing here in the top row, that's considered a minimum rate for aeration. A higher rate could be 10 times that amount or 1 CFM per bushel. And then it, depending on how much airflow you have, impacts the amount of time you need to run the fan to push that air all the way through the top, okay, or pull it down in case of a negative air pressure system. Put together just kind of a rough estimate here, but for a 10,000 bushel bin, if you have a 1 horse fan, you'd be in this ballpark, okay? If you have a 10 horse fan, you'd be in this ballpark, okay? And similar for other bins. But then and then the other piece on this slide is if you have a low amount of airflow, and we don't talk about wintertime aeration so much, or springtime aeration used to be recommended. Now it's you want to keep it cold, and we'll talk about why. But if you have a hot spot, then you may want to run the fans in the spring. It's about the only way you can cool it out. But getting back to the fall, if you're running 150 hours, you have the minimum rate, you want to run that fan continuously. It's going to take about 5 days to get that front all the way through. Okay, and you want to pick a time when the average temperature predicted is the temperature that you want. Then you want to try to cool at about 10 degrees a month. Okay. On the other side, if you have a large fan and you have a little more flexibility when you run the fan, you can run it consecutive days and you can be a little more selective with the times. You'll get closer to the average and the target you want. But the grain is going to hit the average during those fan operating hours. It's going to hit that average temperature. So this is the monthly average temperature for Kentucky. July and around 80 degrees, wintertime is around 35 degrees. So in the fall of the year, we want to start cooling our grain and get it down to below 60 as quickly as we can. Oftentimes we have opportunities in September to do that in the evenings. You'll have several days, consecutive days, you can start the cooling front. You want to continue cooling then again in October, another 50 degrees, down to 50, another 10 degrees, and then all the way down into wintertime, cool it down to about 35 degrees on average, and then you keep it cool. You seal the fans. Leave the roof vents open, but you seal the fans, okay? And that'll keep the grain in the bottom of the bin, keep it cold. and it'll minimize wind-driven air movement through the bin. Okay, so grain's a good insulator, and it'll hold the cold temperatures, and that's shown in this simulation for a very large bin, 135,000 bushel bin. Simulation was run in southern Indiana, so it matches pretty close to Kentucky conditions. I think it's a good comparison for us. And what we're showing in the center of this, okay, the image on the left is temperature changes over time. So it was stored and cooled in the fall, and then this is looking at the end of the simulation in late July. You can see what changes have occurred in that bin. And then on the right side, we're looking at moisture. Okay, so temperature on the left, moisture on the right. And you can see, as I said, grain's a good insulator. It's staying about 40 degrees in a large mass in the center. Along the wall, the floor, well, it's mostly along the wall, it's warming up, but it's not penetrating past the wall very far. Okay? And if you've ever gone into a bin in the summer, you can feel that. And it doesn't extend much a foot past the wall. You can start to feel a temperature change as you go away from that wall. So for that reason, so the other piece of this is, well, how does that change moisture? And it's showing here on the right that it was put in at 14% and it didn't change much. All those 6 months, 9 months of storage. Again, this was simulated with the fans sealed well. The roof was ventilated. You can see he has some heat buildup in the top, but it didn't penetrate below the surface very far, comparatively. And again, just to illustrate, I've seen metal, wood, plywood. You can use heavy plastic or tarps to seal those fans. You just want to keep the air movement out of that area and from warming up those plenums and the floor. So how do you know how much airflow you have in your bin and fan combination? There's a free program that's available at the University of Minnesota. All you need to really know is the size of the bin, the diameter and the height, because that's going to dictate how much airflow you need, but also how much resistance. You can specify desired airflow, or you can put in the fan that you have from a library of about 400 fans that are commercially available across the U.S. Obviously, you need the grain type because that's going to impact how much resistance to airflow. Number of fans, the size, the horsepower, all that. Again, you can select that from a library of fans that are in the program. If you have a 10-horse GSI fan, for example, vane axial, you'll find that on the library. Plug that in, and we'll take a look at an example of what it generates. Okay, so you're going to get bushels, airflow, and you can get it a couple of different forms. This is a screenshot of the input slide, or the input page on the web page, but I know it's kind of hard to read. But what I did, and again, remember I said the average bin sold is about 50,000 bushel. So I selected a 48-foot diameter bin with 33 feet of depth, 33 feet. So it's like basically a 12-ring bin. I specified a design airflow of half a CFM per bushel. I want to see, well, how much airflow or how much horsepower would that take? It's a large bin, and I'm going to go a little on the high side. Okay, it showed that I would need 30 horsepower total. Okay, and because of the depth, we got quite a bit of static pressure. It's predicting about 5 inches. So anytime you're over 4 inches of static pressure, you need a centrifugal fan over a vane axial. Vane axial fans will deliver air up to about 4 inches of static pressure. And more than that, you need a centrifugal fan. So in this case, I selected two 15-horse centrifugal fans out the library. Okay, so I have corn. I have a full perforated floor in the bin, and you could put in individual ducts if you had that. But then what the program gives you is how many bushels in 3-foot increments then, from the top to the bottom to the top, whatever you want to say. How many bushels in 3-foot increments, how much air that those two fans are going to supply at that depth, okay? From that, you just divide your CFM by your bushels, and you get your CFM per bushel, very straightforward. And then it also calculates the static pressure as you fill the bin, okay? So you notice then at the bottom here, when the bin is full, I got my half CFM per bushel, and it was about 5.5 inches of static pressure. The other piece is, it's interesting here, when you're about 20 feet of depth, you have 1 CFM per bushel. So when your grain gets down, when you're emptying the bin, it takes half as long to push that aeration front through at 20 feet than it does at 33. Okay? So you can use that program, put in, see how it impacts for wheat. You just select wheat. Once you've got your set, you can go ahead and generate that real quick. I didn't take time to do that because we have limited time today, but it's very straightforward. Then I recommend it to any farmer that wants to know how much airflow do I have in that bin, and at different depths. And I'll give you all that. So, then the other piece I took from that was to look at 3 different aeration scenarios. Okay? A minimum rate of 1/10 of a CFM per bushel. Take the 3-horse fan, not a very big fan. It's a large bin, but it takes a pretty small fan. Well, what about 1/4 of a CFM per bushel? Well, that'd take a 7.5-horse fan. Now, when you start ramping up the airflow, you're pushing more air through the same size restriction. So static pressure builds up pretty quick, okay? And that's why it's a little more costly. But looking at 10 cents per kilowatt hour, which is a fairly standard rate across the state, I'm looking at 3 aeration cycles for each of the systems. Total cost and then cost per bushel is really inexpensive. 0.3 of a cent for the lower airflow rates and up to 0.6 of a cent per bushel for the higher airflow rate. So you're going to get that done more quickly. It's just a matter of how you want to operate it. They'll all do the job. Got to manage them a little bit differently, but they can all be operated to cool that grain. A little bit different costs involved, so it's up to the operator how he wants to set that up. But it's very affordable insect control. I think you have to agree on that, right? So the other piece we want to talk about is monitoring. And you can use temperature cables to track that airflow rate, track the temperature change as that cooling front is being pushed through the grain bin, right? In time, you'll see, the changes in temperature because those temperature cables are designed. We have a sensor along the cable. These just kind of hang vertically in the bin, and about every 3 feet, you'll have a sensor. They make some humidity sensors as well, which in turn calculate the moisture at that spot, and that's predicated on the equilibrium chart that we showed earlier. There's some other ways to do that. We'll talk about some instruments here. But this just depicts kind of a what we might call a low-end system it's a manual operation where you can plug in your handheld readout device, download all that data. You may have to write that down or put it in a spreadsheet to track it, or you can get some more sophisticated programs that'll do that. You can track it. You have these blue dots represent the temperature cables, and again, you have those sensors every 3 feet. This is a fairly large bin, but this image on the lower left of the slide is showing the array of cables in that bin, okay? And you just dial through those. You can use a computer program to select those and then read the temperatures in each cable. And you can get quite sophisticated. You can look at changes in temperature over time. You can see where our cooling front was pushed through. You can track fan hours. You can hook it up with a weather station and track weather conditions and use that information to guide your aeration strategy. Okay, so it's getting kind of sophisticated, and obviously a little more cost involved. But back to the value, if you got 500,000 bushels sitting in, or $500,000 worth of grain in that bin, probably a good idea to spend a little money on monitoring it. A low end, back to the low end cost, low end or low cost systems. This is an insect trap that we've used for some just monitoring work in work I've done with entomologists. It's just a plastic tube that has holes drilled all the way to the perimeter, and you insert these vertically in the grain around the surface, different spots. Just a natural movement of insects they'll find their way into that tube, and then they'll follow it down into this trap where you can just extract that on a weekly basis, collect your sample, put it in the bag, take it to the lab, and see what kind of insects you have. We did that for a study with Kansas State some years ago, and looking at farm bins and elevators. A little more sophisticated version of that insect trap is shown here. This is an electronic version. We have a little infrared sensor actually down here. Not only does it detect how many insects you have, but it's been calibrated to measure the size and detect the size. And with that small of a high-end beam, you can actually do that. And it's been proven with the entomology work in the USDA lab at Kansas. But this is the same idea as a temperature cable. You can walk along with a handheld device in each bin, download that data, what's happened since you checked it last time. It's a good idea to check that weekly, I think. And then this, on the same vein, this is an electronic, insect detection probe. And it's got a cable on it, then you can hook to a laptop. Feed that information in, you can record that automatically and track it and look at the history and the record of that. You can access that through a cell phone. You can be in, some farmers today are vacationing in Florida, right? In the wintertime, and they want to check their grain, but they can do that. You don't have to have somebody go on top of the bin. Very sophisticated. And then the last piece of technology I'll talk about is a CO2 monitor. Not too many people have heard about these, but they were first researched at Purdue, and I was really kind of skeptical because I thought you've got such a diffuse environment there. Can it be that sensitive? And it turns out, yes, it can. And actually, a CO2 sensor will detect off gas from insect activity, just respiration of the grain. When it starts to spoil, it generates more CO2. You can pick that up quicker than you can a temperature change. So then you can get ahead of the game because that's a more diffuse measurement. So you would check that in the headspace of the grain bin or at the exhaust fan of a grain pile. If the CO2 starts increasing, maybe I need to go in there and check some things more closely. Maybe I need to move that grain, disperse it, sell it, move it, get it off the property, or sell it and get it out of there. But the CO2 sensor can be quite useful for that. And again, it can help you monitor the environment, I think, a little more with more reliability. Okay, so now we're getting to some of the instruments that are commercially available for monitoring grain. This one in the upper right is one I saw at the machinery show just last month. It's a $400 device. It actually just turns on a fan on and off that's programmed for the temperature. So you can dial it down each month, run the aeration fan. You can monitor that with your cell phone if you have a Wi-Fi connection on the site. And all these have that same capability in these days. But so that's kind of your low-end system. There's a website for that. GSI has bought the Bullseye, which was actually made by the same guy that made the switch. But the Bullseye monitor is a little more sophisticated. It connects the temperature cables with either manual or automated readout. And then on the bottom here we have a couple of different systems that are widely advertised in farm magazines, the IntelliAir system and the StoreMax program. Same kind of thing. They're detecting hotspots. They're detecting, maybe in the case of the StoreMax, insect activity. But they're running the aeration fans based on the condition that you program into the system. Okay? And then you can monitor those remotely. So then there's a list of, and the websites, I checked the websites, these are active. Okay? But different companies that make these kinds of systems. Okay? And in terms of cost, generally, obviously in general terms, the manual systems are lower cost than the fully automated systems, and then you can get kind of a hybrid that's in between. So I think it's a cost to fit any interest level of need there. And just to break down on cables versus controls versus fully automated systems, this was put together by a colleague in Oklahoma State. But again, the temperature cables, they're a good place to start, but you can have a hotspot. If it's away from the sensor, it won't detect it until that hotspot gets quite large, right? That's why I like the CO2 monitors in addition to the temperature cables. I like both of them. At the same time, I think you can't afford to put enough temperature cables. You want a high density in that bin, ideally, right? So the CO2 sensor can actually help compensate for some of that. But it's better than nothing. We have a lot of stored grain without any monitoring equipment in them at all. The newer systems, the larger systems, have temperature cables, and they have the more sophisticated aeration systems go along with them. To switch from that more conventional storage scenario to temporary storage. I'm going to go through this fairly quickly, but now we're talking about these large outdoor piles that are with a soft cover or a horizontal warehouse, or maybe as a machinery shed that you're going to modify to store grain in. Several considerations. Obviously, you want the cost. What's it going to cost you maybe you reinforce the wall, for example. Maybe redesign the floor, rework the floor so you can have better condition and better environment for storage. You want to think about storage capacity. I mean, it plays with the economics, and I do have a calculator on the website that will generate the number of bushels you can store in. And we'll take a look at an example. Next slide. But you want to think about, certainly the structural integrity of the walls. Can it withstand the grain pressure that we want to push that wall out? Do you need to reinforce the wall? Okay, that's where engineering comes in. But picture I'm showing here on the right is actually over in Christian County, where they've reinforced the wall, added some studs in behind that plywood sheeting, and they've got a 4-foot wall you can build fairly affordably in a flat storage or a warehouse or a storage shed there. You see those aeration tubes that are pushed over to the side. This is before they started becoming active, but that was right before harvest time when I took that picture. And you do want to think about aeration in flat storage, because that gives you that, back to that storage life slide, gives you some storage life by cooling it out. Obviously, you want to protect as much as you can from the elements. You have a lot of exposure in the pile, and you want to protect it from birds and rodents as much as you can as well, because it's got a lot of exposure. I mentioned the website, and again, it's shown here, but we'll just look at some examples here. The top 2 rows show a 40 by 60 foot building without a wall reinforced, okay? And then the center peak is going to be 8.5 feet. Need that for planting purposes, but the total bushel is around 5,560 bushel. If you can just bump the wall height up 4 feet, that's going to impact the peak height as well, of course, accordingly. But then you can get 13,000 bushels in that bin, or in that shed. And then similar values here for the 60 by 100 foot. So again, all you need to put in for that on the website, all you need to put in is the size of the structure, the internal dimensions of it. And it'll bang out not only the peak height, which is useful for planting, but also the amount of bushels, which most people are interested in. And then what I plugged in a 0.2 of a CFM per bushel to give you an idea of how much airflow you need through that pile. And it's just an illustration. A 40-foot wide building, your aeration tubes would be about 15 feet apart in the center, and you want to you may want to wiggle those around a little bit depending on what kind of auger you have or device you're using to fill the building. So plan around that. But for the most part, the surface of any grain pile is going to be a 5/12 slope, okay? And that's useful for planting as well. Last couple of systems we'll look at here as we close out. There was some interest some years ago in covered outdoor piles. I liked them for several reasons. One is because you can kind of make a modified, like you would for hay storage, kind of a granular or a gravel surface. It's well packed, but you can lay in an aeration tube at the base of that before you start to fill it. So this is just a 5-foot ring. In this case, it's a 90-foot diameter ring. After it's generally filled with a portable auger, you may have to have an extension on that because it's a fairly wide pile. But then you've got a custom-made cover that fits that shape. Okay, it's sized to the ring, and you place that on. Then you turn the fan on. It holds the cover down, and the wind won't blow it off. So that's showing it after it's filled, and then with the cover here on the lower left, and then unloading. They unloaded that with a track hoe, essentially. Took them, I think, maybe 5 minutes to load a truck, they were saying. And then after they got it emptied away from the wall, they went in with a loader that they had on site. So between those two, you can load a truck pretty quickly. And the last thing we want to take a look at here are grain bags. We've seen a lot more interest in those, especially last year where we had a big crop. Late in the harvest, grain was drying down fairly well. Not in every case, but where it was dry enough, I think these were a good selection. And again, you would want to put corn in there 15%, no higher, I think, and as cool as possible, okay? But you can unload a truck, or a grain cart in this case, just in a matter of a few minutes. And it takes special equipment to fill that bag and then offload it. But at the same time, the bags themselves, I think, cost about $0.05 a bushel for storage. Okay, So it's very affordable storage. And this picture was taken on the bottom. They had numerous, I think they had 300,000 bushel total in this site, in the bags. And I've seen some larger piles. I've seen smaller ones. But I think it's a good choice for late in the season. And in this case last year, he wasn't really planning on using that. But when he started combining, he saw he had a bigger crop than he expected. So it's another place they fit in well because obviously the portability of that fits in well with a lot of, especially when you're running a lot of rented ground. So to summarize, I've made some of these points before, and I know we're running out of time here. Back to inspection, some of these tools can help you with that chore a lot more easily. Okay. Back to the website, just as we close out, some of the information we have there, in addition to what we talked about, I've got some energy calculators on there for grain dryers that I've done a lot of work on that in the last few years too. Okay. Resources, a lot of land-grant universities have post-harvest engineering programs that are active. I don't have them all listed here, but those are ones that I've worked with. And we've worked together to put together an update on the grain drying and handling and storage handbook at the Midwest Plan Service. This is the second most popular publication that they print, and it's widely used in ag mech programs around the country. So the last edition was '87, so it was a little overdue, but we finally got it done last year. And then there's some other resources, again, the Midwest Plan Service listed here, but the USDA Grain Lab, they do a lot of work, a lot of research work on insect dynamics. Of course, the parent society of our profession, American Society of Agricultural and Biological Engineers, I cited some of their data through this presentation. The GEEPS is the Grain Elevators and Processors Society. A lot of the other states that have more storage have very active chapters. And again, they have online programs for drying, handling, safety aspects that relate to grain systems. Very useful. And then I could go on with a list of trade magazines, but you're well aware of those. So my contact information. So with that, I'll take any questions if you have, and I thank you for your attention.